Today we're going to start looking at clustering algorithms. I'm going to give a brief introduction to the idea of clustering and compare it to classification, which is what we've been looking at mostly so far in supervised learning. And then I'm going to start with this k-means algorithm for clustering and give you a first look at the expectation maximization approach framework that we're going to look at in more detail in future, but now just to get a first informal notion, intuitive notion of this algorithm, and also to help us understand the relation between clustering and classification. So let's start with this idea. The basic idea of clustering is that we want to group similar things together. So we want to find groups in our data, in our examples, in a way that represents their similarity. But as you can imagine, these are somewhat vague concepts, because what is similarity? What do we mean by grouping together, or what are the criteria to group them together? So we'll start to look at these problems that arise when we have this goal of grouping similar things together. In this case, when we look at this example, it's very intuitive that we could form three groups. So these would be the groups that we have here. We have this cloud of points that belong together, and then these two smaller clouds here. If you look at data in 2 dimensions, it is often quite intuitive to determine these groups, but even in 2 dimensions, sometimes we are not quite sure how to group the examples. And in practice, when we have data in 4, 5, 6 dimensions, then we cannot even look at the data like this to find groups. And so one important aspect of clustering algorithms is this exercise of formalizing, of making concrete and specific what are the criteria for grouping things together, what are the measures that we use to determine their similarities, and then the algorithms that we follow to find these groups. So things that we can use is to have some similarity measure that we want to maximize within clusters, or alternatively, we may be looking at some difference measure. And in that case, we want to minimize differences within clusters. Note that this difference can be, for example, a distance, but it can be something else. But either way, we want to make it so that within clusters are the examples that go together, that are more similar or less different. And between clusters, we have the most difference or the smallest similarity. So different clusters will be composed of more different examples between them. And this is something that the implication of this is that clustering always requires some measure either of similarity or of difference. It doesn't matter if we use similarity or difference, because we are just looking at the same idea from different perspectives, but we must be able to tell that some examples are more alike and some examples are less alike. And the way we measure this and the whole the choice of algorithms for clustering will depend very much on what we want to do. So the general idea is that we want to understand the data better. We want to find, for example, patterns where we can imagine the data as groups that we put together. And so we are conceptually at least reducing the data to these relevant groups here. This may be to see to help us understand the data, to help us deal with abundant data, because we may not want to deal with all the examples individually, but group them together and then just look at the groups and so on. So basically, the reason for clustering is, broadly speaking, to put things that are alike together and help us understand when the data is very complex. But in practice, in detail, depending on the application, we may have different purposes for clustering. And thinking about exactly why we want to do clustering is an important step then for choosing the similarity measures, for choosing the algorithms and so forth. So this is a classical example of clustering. This is Darwin's tree of life. We have here the I think note that he left, and he tried to represent what would be the relations during evolution between ancestral species and species that exist today. So species today would be at the leaves of this tree, and then we have clusters, similar species together, and then clusters of clusters. And this is an example of hierarchical clustering, where we are creating groups and then groups of groups and larger groups and so on. And we have this tree of all living organisms that is broken down in these subclusters, in these subgroups. A more recent example is this paper that identifies cities and apartment blocks and large regions in China that have, in theory, people living there, because the apartments are owned by people. They have been built, they are owned by people. But what they did was to use mobile phone data in different applications, and then cluster them, the positions where the mobile phones are found during the day according to density. And so they found that there were large regions in many cities where people were hardly ever found. So even though there are lots of apartments there, and there are people who own those apartments, they are never there. And so these are what they call ghost cities, which have no one around. And these were identified by looking at density-based clustering of the locations of the mobile phones. So these are some examples, but basically when we want to cluster, we generally want to obtain some summary of the data. We can think of it as this general idea, because you can think of all the different organisms that we have, but we can group them in species and then see the relations between the species and ancestral species and so on, or take the data from all, millions and millions of mobile phones, and then find groups where there are large densities or small densities of mobile phones. So there we can think of this general idea, but then in some specific cases we may actually want to do this reduction, for example, for improving performance or for finding representatives or things like that. So clustering in general looks for these patterns by grouping examples together. So it allows us to look at the patterns in the data on a coarser scale, where we just ignore the individual differences between the examples and we look at how they are grouped together in these clusters. But we may actually use this to simplify the data. For example, suppose that we have these clouds of points in blue here, but there are too many points. We want to keep the same shape of the data, but we want to use fewer points for that, because we want to optimize some process, or we don't want to use so many of them to save memory or something like that. So we could use a clustering algorithm that could give a result like this and give us representatives that are spread out, have a distribution that is similar to the original points that we have, but that's a smaller set of points, and they still give the same kind of shape that we had, and we can control how many we keep, if we want more of them, if you want fewer of them. So we can use this kind of these clustering algorithms for this kind of purpose too. And I'm going to show a particular example of this using k-means. But in general, regardless of why we want to cluster the algorithms, there is also the question of how we are going to cluster them. How do we decide how to group the examples? For example, take this distribution of points. We could say that there are two clusters here. We have a set of points over here and another set here that we are marking with red circles and green triangles. But we could say that there are three clusters, because these four are really not quite as distributed as these here. So we could separate these circles, the squares and the triangles, or maybe separate a bit more, these three here, or maybe single out these two. So how many clusters we have here is not something that we can rely on the data itself just to specify. And this is something that you will find in general in clustering algorithms, that even though many clustering algorithms can give you different numbers of clusters depending on the patterns of the data, the numbers of clusters will also depend on the parameters that we specify to determine how propense the algorithm is to give us more clusters or fewer clusters. So there is this problem that depending on what we tell the algorithm, we often get different numbers of clusters, and this is not necessarily wrong because it depends on how we want to interpret the data, what our criteria are for clustering the examples. So there are several things we need to decide when defining our clusters. First of all, how are we going to split the data into clusters? Are we going to do partitional clustering? For example, something like this. We take all the data points and we separate them into different clusters. This would be an example of partitional clustering. Or we can do hierarchical clustering, which is to create clusters that have subclusters and subclusters in a tree. For example, like this. We have this green cluster here and the red cluster here, but the red cluster is subdivided into three clusters: the squares, these hexagons, and the circles. And the green cluster is divided into the two types of triangles. So this is an example of hierarchical clustering, where we have clusters that are that have then subclusters and so on. So this is one important decision, because depending on the kind of data that we have, it may be more relevant to do hierarchical clustering or partitional clustering. Going back to these two examples I showed, if we are looking at the evolutionary relations between species, it makes sense to have a hierarchical clustering, because we have species that descend from ancestors and then groups of ancestors that have an earlier common ancestor and so on. But if we are looking at the distribution of people in cities to find those ghost blocks or ghost cities, then it doesn't make much sense to do a hierarchical clustering. It makes more sense to do a partitional clustering, because we are just looking for the regions where there are large groups of people or where there are fewer people. So this is one important decision to make, whether we want to have just a single layer of clusters, so to speak, or to have clusters with subclusters. Another decision we need to make is how the membership of each example will be constrained. Are we going to demand exclusivity, that is, each example belongs to only one cluster, or are we going to assign examples to more than one group? If we are going to assign them to more than one group, then maybe we want to have some fractional measure of assignment. This is what happens with fuzzy clustering, where each example can belong more or less to a cluster with a continuous membership value that goes from 0 to 1. Or we can do probabilistic clustering, where we do something similar. We also have these membership values, but the membership values are probabilities. So each example will belong to several clusters with different probabilities, but the probabilities must all add up to 1, because it must be somewhere. The probability of being in any cluster will be 1. Then we need to also determine if we are going to cluster all the examples, or if we are going to leave some examples out. So in the case of complete clustering, all examples are assigned to clusters, at least one cluster. In the case of non-exclusive clustering, it can be more than one cluster. With partial clustering, we leave out some examples. For instance, if we consider that they are noise or irrelevant or something like that, we may discard them as not belonging to any cluster. So as you can imagine, if we are thinking about these different criteria, we will end up with needing very different algorithms to do clustering in these different conditions. So that's what we're going to look at in the next few weeks, different algorithms that allow us to cover these different needs, and we need to select them according to what we want to do with our data. Then there are other characteristics that we can find either from the data or from the interaction of the data with the parameters that we impose. In the data, we can see if the data gives us well-separated clusters, which means that examples within each cluster are more similar to each other than they are two examples on different clusters. So these would be well separated. But this may also depend on how we cluster them. For example, if we were to cluster these two groups into one cluster and this in another, then this one would be a bit strange because there would be a large dissimilarity between examples in this first part, and so we could end up with clusters that are not as well separated. The kind of algorithm that we use also determines the types of clusters that we're going to create. For example, we may have prototype-based clusters that are based on distance. For instance, each of these clusters is determined by a prototype, one point in our feature space that marks the center of the cluster, and each point then is assigned to the closest prototype. So this means that the partition of the space is done based on the distance to the prototypes. We can have, for example, contiguity-based clustering, where clusters are defined by finding examples that are closer to each other. So we can imagine, for example, a network of relations here, bringing these points together and bringing these points into a different cluster. We can have density-based clustering, where we identify regions where we have a large density of examples, and these mark the clusters. And then where we have low density, this can be discarded as noise. So we're going to see different algorithms that do clustering in different ways to capture different forms of thinking about the clusters that we want. So basically, if you want to use clustering, you need to think about what you want to use clustering for. In general, you want to use clustering to help you understand the data, to help you extract some pattern from the data, simplify something, look at the overall relations between the examples, something like that. But you need to think also of this in detail to select the algorithm and select the criteria you're going to use. So how can you compare examples? If we have points in 2 dimensions like this with continuous values, we can easily use Euclidean distance. But you can have different types of things, for example, text documents or images or sound files or something like that. You need some measure of similarity or difference between the examples in order to use clustering. Then you need to think about how the examples relate to clusters. Does each example belong to only one cluster? Can the examples belong partially to some clusters? Can some examples not belong to clusters at all? So you need to think about, for the purposes that you have, how the examples relate to the clusters. Then you need to think about what is the best way of grouping the examples together. Shall we look at the density of the examples in the space of the features? Shall we look at how close examples are together or two examples in common? Or look at prototypes that represent groups of examples and so on? And then we have this problem of validating the clusters. Are these clusters useful? Are these the correct clusters that we're trying to find? So as you can imagine, this can often be a quite complex problem because it requires that we think about all of these details. Of course, you can not think about these details, just pick a clustering algorithm, but remember that when you do that, you are implicitly making these choices, even if you don't know you are making these choices. So here the danger of having some result that is completely wrong, at least according to what you want to obtain, is considerably higher even than with supervised learning. So it's important that you really think about these problems when you are choosing and applying clustering algorithms. Now, there are differences and similarities between clustering and classification. You can think that in classification we also have examples in different groups, and we are trying to predict which group an example will belong to. In clustering, we are also trying to put the examples in different groups. However, the big difference is that with classification, the groups are labeled in the training data, so that we can measure the error in predicting where each point will belong. So this is why we use supervised learning for classification. In clustering, we cannot really define this, measure this error, because we don't have the clusters in the data. And also, the goal here is not so much to predict what cluster a point belongs to, but try to use clustering to identify some pattern, something that we want to understand. So the way we are going to cluster and why we want to cluster will depend a lot on these issues. But basically, you can think of clustering as a problem where we want to find some classes for the points, some groups where we want to place our examples, but these groups do not exist in the data. We are basically creating them, inventing them in our model when we are clustering the points. So this makes clustering very different from classification, even though the end result may look superficially similar, in that we are assigning points to groups, to clusters, classes, whatever. Okay, so let's see a concrete example, k-means, one clustering algorithm that is very easy to understand, so it's a good starting point for this. We want to find the best clustering, that is the best group of clusters for k clusters, where k is a number that we define initially. And we want to specify these clusters by proximity to the mean point of the cluster. So we can imagine that the mean point of a cluster is a representative of all points that belong to the cluster, and each point will belong to that cluster that has the closest mean point. So this k, the number of centroids, the number of these mean points that we are going to use, is predefined by the user. And this is a clustering that is partitional. We don't have subclusters. They are all at the same level. It's exclusive because each point will only belong to one cluster. It's complete because there are no points that are left outside the clusters. And it's based on this prototype. So these centroids, the mean points, are vectors that are like the examples that we use. They are not any particular example, but they have the same features. And they serve as prototypes for the cluster. So this is the representative of the whole cluster. And we're going to use this Lloyd's algorithm for computing these clusters, which consists of starting with a random set of centroids, and then assigning each example to the closest centroid. After this, we have the clusters defined, and so we can update the centroid, the position, to the mean point of each cluster. And then we're going to recompute until we have convergence. So let's see this more visually. It's better to help understand. Let's suppose we have this data. Now, the first step we need to do is to start with some initial guess for our centroids. This 4G method for initialization starts with coordinates of randomly chosen examples. For example, we choose 5 like this. We have 2 here, 1 here. So these would be the random initial positions of the centroids. Another alternative, so after we do this, we assign examples to each centroid. So here we have this hexagon and the triangle. They are very close together, but the triangle is more on this side, the hexagon here, then the circle, the red circle here, this purple triangle here, and the blue square. So these are the 5 initial clusters that we can create by choosing points at random. Another example of initialization is to assign at random each example to a different cluster. So this one is a green triangle, a blue hexagon, a red circle, and so on. We do this at random. And now we compute the representatives, the centroids of all these clusters by computing the mean coordinate or the mean point of each of these clusters. So this random partition method tends to aggregate the initial position of the centroids more to the middle of the cloud of points that we have in our data, whereas the Forgy method tends to spread out the initial position of the centroids at random in our data. But this is the first step. We are starting with an initial guess of where the centroids are. And now what we're going to do is to iteratively apply the Lloyd's algorithm to find the position of the centroids where everything converged and there are no longer any changes. So let's see how that looks like. We start, for example, with the Forgy initialization. We start with these 5 initial centroids. We compute the clusters by assigning each point to the closest centroid. And now we're going to compute the midpoint, the mean of the coordinates of each cluster. So for example, this triangles cluster, the mean point is here. For the squares, the blue squares, the mean point is here, and so on. Now that we have the mean point of the cluster, we are going to move the centroid to that mean point and reassign the points to the clusters. So you see, as we moved this triangle over here to the center, now these points will belong to the circle cluster and not the triangle. So we changed a bit the membership of the examples because the central points moved. And now we're going to do this again. Since the membership changed, we can recompute the means again, and then update the centroids, recompute the means, update the centroids, and keep doing this until we reach a stage where there are no more changes in membership of the clusters. So when that happens, the mean points will no longer change and we have convergence. The algorithm stops. So this is how Lloyd's algorithm works to find the k-means, the clusters by this k-means method. So looking a bit more detail, you will not need to implement this, but I'm going to show the code just to look at this algorithm in detail. One thing that we need to do is to find the closest centroid to each point in our data. So we can start by creating an array of labels. These labels indicate which cluster each point belongs to in our data. So let's imagine that our data is a matrix with each example in a row. So each feature is a different column and all the examples are different rows. So data shape 0 will be the number of rows. This is the number of examples, and we need to have as many labels as the examples. So we create this vector, and now for each row in our table, or for the index of each example, we are going to compute the distances between all the centroids and this point. So this is done by subtracting the coordinates, squaring the coordinates, and computing the sum. This is the Euclidean distance, or more specifically, this is the square of the Euclidean distance, but we don't need the square root because now we're just going to find the one with the smallest distance. So this argmin function gives you the index of the smallest value in a vector. This vector is the vector of distances between this point and all the centroids. So this is the index of the centroid that is closest to the point. And this will be the label for this point. So this way we can assign all our examples to the closest centroid. We also need, during the algorithm, to move each centroid to the midpoint of the examples that belong to that cluster. So we are going to get the labels for all the points in our data. And now for each of the centroids, we are going to change the coordinates of that centroid to be the mean of the coordinates of the points that belong to that particular centroid. So this condition here is specifying that the label for the points must be the index of this centroid. And now we are computing the midpoint of those coordinates and assigning that to this particular centroid. So if we have this, we can start with some initialization. For example, with Forgy, we shuffle the indexes for our data, and we return as the coordinates of the centroids a copy of the points at those randomly selected indexes. So if we need k centroids, we choose k points, and note that we are shuffling so that we are not picking the same point twice. So this is not just random selection with reposition, it's a shuffling of the indexes so that there are no repetitions in selecting these initial points. Alternatively, we can assign all our data points at random to any of the k clusters, and then we just compute the midpoint for each of these random cluster, and this would be the random partition initialization. So for the k-means algorithm, then we would just iterate this until convergence, moving the centroids and attributing the points to the centroids. And the question here is how can we find these prototypes and find the position for the prototype. So in general, we are going to use Euclidean distance. This is the most typical choice, but you can generalize this and use any of the Minkowski metrics. So basically, the difference between the coordinates, the absolute value of that difference is raised to some p, and then the p root of that. So if p equals 2, this is Euclidean distance. If p equals 1, this is Manhattan distance. And now you can think of different distances to use. But generally, Euclidean distance is what is most used. You can also think of k-means conceptually as very similar to a self-organizing map that we saw previously, but without the topology of the network. So these vectors, the centroids, are really independent of each other. Now, one problem with k-means is that we need to compute the midpoint of examples. If we have examples that are like this, that are coordinates in some space, then it's easy to compute the midpoint and find the representative. However, it may happen that we cannot really find the midpoint. We have some way of measuring distances or similarities, but we cannot measure the midpoint. For example, suppose that you are comparing text documents. We can have some measure of how similar two text documents are or how different they are. So we could convert this into some kind of distance measure and try to find the closest ones to a prototype and so on. But we cannot really compute the average of text documents. There is no good way of finding the mean point between text documents. So one variant of k-means is called k-medoids, where the prototypes are always specific data points. These are called the medoids. They are not the means of the clusters, but they are examples that are as close as possible to some center of the cluster. And the advantage here is that we only need to have some measurement of dissimilarity between the examples. For example, how dissimilar, how different text documents are if we were trying to cluster them. And then we are going to, for each cluster, we are going to find the best example to represent that cluster. And this would be the one that is closest to, on average, to all the other examples on the cluster. So this is similar to k-means. We are also recomputing the clusters, finding the prototype and so on, but we don't compute the mean. We find an example within the cluster that is closest to all the other examples, so that is more representative of the cluster. So let's use the k-means algorithm to take a first look at this very important foundational algorithm for clustering and for in general, for unsupervised learnings, the expectation maximization algorithm is very used. So let's suppose that we have a set of observed data which are the features of our examples. So this is the X. Remember, in supervised learning, we also had the class labels in classification, or in regression, some continuous value that we wanted to predict that we called Y. In this case, we don't have that. There are some clusters, but they are not present in the data. So we call them latent variables. This Z will be the clusters that we want to assign the points to, but it's missing from the data. We cannot observe it. And we also have parameters for our model. For example, the positions of the centroids in k-means, in the k-means algorithm. Now we want to find the best parameters by maximizing the likelihood. The likelihood would be the probability of all the data, so the X and the Z, the features and the clusters, given our parameters. And this is what we want to maximize, exactly like we did with supervised learning. However, there is this big difference. In classification, these classes, the Y values, are determined by observing something in nature, so they are present in the training set, in the data. In clustering, these classes are part of the model. They are not present in the data, so they are the cluster labels that the model is trying to discover or invent by looking at a pattern in the data. So you can think of clustering as a sort of classification problem, but without the classes being specified in the data. We need to create them, we need to make them up in our model. So this is why we have a problem here, because if we want to find the parameters that maximize the probability of X and Z, we need to know X and Z. Otherwise, we don't have a way of maximizing this. Okay, so the expectation maximization algorithm tries to solve this. Let's think of this as what would be hypothetically the complete data. We have the X, which are the features, the coordinates of the points, and we also have Z, which is the assignment to different clusters. These points belong to the red cluster, the green cluster, the blue cluster. But actually what we have in the data is this. Only the coordinates of the points, only the features. Because these Z values, these clusters, do not really exist in the data. They are being created by our model as it tries to help us understand the data. So we cannot really compute the likelihood of our parameters for the whole data because we don't know Z. So we cannot compute the probability of joint probability of X and Z. So if you go back here, this would be the probability of a point being in this position and belonging to the red cluster, or a point being in this position and belonging to the green cluster, and so on. We cannot really compute those probabilities directly like we did in classification, because in classification we had these values. But we can try to estimate some posterior probability of Z if we have some guess for the parameters and X. So if we have some guess of the parameters of our model and the positions of the points, for example, suppose in k-means the parameters of our model will be the positions of the centroids. If we have a guess of the positions of the centroids and the coordinates of the points, we can try to estimate to which cluster each point belongs to. So this is the way we can solve the problem of not knowing Z to try to find our parameters. We can start with some parameters and use that to estimate Z. And that is the general idea here of the expectation maximization algorithm. We're going to see this in more detail, more formally, when we look at probabilistic clustering. But even with this simple example of k-means, we can understand the intuition. So in abstract, we can think of this. We need the probability of X and Z as a function of our parameters because we want to maximize this, since this is the likelihood of the parameters. But since we don't have Z, we are going to write this function, the likelihood function, for some expected value of Z given that the coordinates, the features that we have for the data, and some previous guess of what the parameters would be. So this would be the expectation step. Using some previous guess of the parameters of our model, we're going to find out what is the likelihood function based on some expected value for z. And now we're going to maximize this likelihood function. So we're going to maximize this likelihood function, so the logarithm of the joint probability of x and z given our parameters, using the z values that are expected according to the previous iteration, to the previous values of our parameters, and we are going to maximize this to obtain the new set of parameters. And now we can repeat this until we reach convergence. So this is the basic idea of expectation maximization algorithm. We can see this intuitive notion in k-means. Even though k-means is not a probabilistic algorithm, so if we are going to be rigorous, this is not exactly expectation maximization, we can see the idea here. So let's suppose that what we want to do is to find the minimum of this objective function, which is for each point in our data and for each cluster, we are going to compute the difference of the point to the centroid of each cluster. This this RNK function here is just 0 or 1. It's 1 if point n belongs to cluster K and 0 otherwise. So basically what we're doing here is just adding the distances, or the squared distance, between each point and the centroid of each cluster for all the points and all clusters. But we are only considering the points and the clusters they belong to. So if we want to minimize this, we can first start by assigning each point to the closest centroid. So this would be, if we want to minimize this, we can expect that it's best to have each point assigned to the closest centroid, because that way we minimize this distance. So this would be the expectation step. We don't know where each point is assigned to, that's not present in the data, but we can, using the current set of parameters, the current centroids, assign each point to the one that is closest to that point. So this is how we determine this function of where each point belongs to, by assigning each example to the closest centroid. And now that we assigned to the closest centroid, we can find the position of the centroid that minimizes this function by just taking the mean position of all the points that belong to that cluster. So basically this is where the derivative of this is 0, and the minimum point is where the centroid is exactly at the mean value of all the points in the cluster. So you can see this is precisely Lloyd's algorithm for k-means, which is assign each point to the closest centroid, and this would be the expectation step where we estimate the z values, those hidden variables, which are the assignment to the clusters, based on the old parameters that we have for our model, so based on the current position of the centroids. And then we have the maximization step, where we maximize the likelihood by finding the new position for the centroids that best fits that assignment of the clusters. So this is the general idea how we can solve this problem that is similar to a classification problem where we maximize the likelihood, but with this added complication that we don't have z. So in classification, we simply maximize the likelihood of our data, the joint of our data given the parameters, so these probabilities. But in the case of clustering, we need to have this expectation step, because the part of the data that we're trying to use for maximizing likelihood is not visible. They are hidden variables in our model that we need to estimate. Okay, so k-means is almost the expectation maximization. The difference here is that we are not dealing with probabilities, but we can find a parallel there and the same kind of idea. We are estimating cluster assignment from the current position of the centroids, and this gives us this likelihood function that we can maximize by placing the centroids in the mean position of each cluster. We'll see this better with Gaussian mixture models because those are really probabilistic models where this can be looked at with more rigor. So let's see an example of application of k-means. K-means historically comes from vector quantization, which is a technique used in signal compression, and it consists in converting continuous values to ranges, to a discrete set of ranges, of clusters, so to speak, if we are looking at it from a perspective of clustering. So this is an example, an image example from Wikipedia, and you have this demonstration on scikit-learn. You're going to do something similar on the tutorial too. So one advantage of this image is that it only has red and green. There is no blue. So we can look at the color channels of this image in just 2 dimensions instead of three dimensions. So if you take all the pixels in this image and look at the red and green component, we can draw this graph where we have the black pixels here. They have 0 red and 0 green. There are some yellow pixels here that have lots of red and lots of green, so this mixture is yellow, and then there are lots of them in between. So this plot is the plot of all the pixels in this image represented in the coordinates of their red and green components. We can do this easily in this image because we don't have the blue component. It's 0 for all pixels. If we had blue colors, then we would need a 3-dimensional plot to see this. You're going to do that in the tutorial, but this one is simpler for understanding these steps. Okay, so how can you do that? We're going to use scikit-image. You have this installed by default with Anaconda, and you have this ImSave, ImRead, which are for images, for reading images and saving images. Basically, this allows you to read images in different formats into NumPy arrays. So when we use emread for the image file, we get this 3-dimensional array that has the width of the image, the height of the image in pixels, and then the depth is equal to 3, because those are the 3 color channels, red, green, and blue. We can reshape this. We're going to divide this by 255. So we're going to convert this into floating point numbers between 0 and 1. This is because each color channel in this PNG file is 1 byte. So it has values from 0 to 255 in integer, but we're going to convert it into 0 and 1 so that we can plot the chart like this. And we're going to reshape this to get a matrix that has as many rows as the number of pixels, so the width times the height of the image, and as many columns as the color depth. So it's going to have 3 columns, red, green, and blue. However, for our particular array, we only need the first 2 columns because we only need to look at red and green since blue is always 0. So we're going to get this array, this matrix. Now we create a figure and we plot these points here. If you want to plot a series of points all with different colors, you can use the scatter from pyplot, the scatter command. You give the x values, which is the first column, the y values, the second column, so red and green components, and then you can give a list of colors where each color can be defined as red, green, and blue. So we're going to just take the colors from the original image, give that as a list, and this will plot all our points like this with the different colors. So basically this is just a code to load the image and look at the data. Okay, so now we're going to use scikit-learn to cluster this and find 64 centroids. So let's reduce this to only 64 colors representative of all these colors in the image. We can use the k-means object from scikit-learn, so you can just import this from the cluster module. You import the k-means class. We create an object of this class by specifying the number of clusters, so in this case 64, and we can just fit our data. So our data is this array that we created, looking only at the red and green components of our colors. So it's a matrix that has as many rows as the pixels in the image and 2 columns for the red and green channels. So now we can predict the label of each of these pixels. Note that when we fit, what k-means does is compute the centroids for the 64 clusters. When we call predict, it's going to tell us what is the nearest cluster or the nearest centroid, so the cluster each point belongs to. So we give the same set of coordinates. We have which cluster each point belongs to. And now we can go here in cluster centers with this underscore. This gives us an array with the positions of all the centroids, and we can plot that in our chart. So this is to plot the cluster centroids. There are 2 scatter commands, because I'm plotting one in black, once in black and then in white with a slightly smaller size, just to make this effect that I have the black crosses and the white crosses inside. But basically this is just plotting the position of the centroids. So this is what we have as a result. We took the coordinates that are given by the red and green components, we compute the centroid positions, and now we can assign the color of each pixel to the color of the centroid. So we can convert all the pixels into just 64 colors. We can do that easily by going through all our pixels and setting the color of each pixel, the red and green component, to the coordinate of that centroid, of the centroid that for the cluster the pixel belongs to. So this will reduce the initial image that has 24 bits per color, so it's 3 bytes for red, green and blue, and it converts only to 64 different colors, so 6 bits. And you can see that we don't lose much resolution here when we do this conversion, and because this number of clusters is enough so that there is not much difference between the original color and the one that we get after clustering. We can do this with fewer centroids, for example 8 centroids. These are the position of the centroids. Then we assign the colors to the centroids. Now all these pixels were assigned the color of this particular combination of red and green, all of these to this particular combination, and so on. So we have only 8 different colors in our image, and now you can see that there is some loss in color resolution, but still the image is easily recognizable. So now we are only using 3 bits for the colors. Of course, when you save the image, you will not notice a reduction in size, because then the PNG format does not take this into account and just uses all the colors. But in theory, you could reduce the data to only these 8 different levels. So this is one example. Vector quantization is one example of using clustering to simplify the data and to reduce the range of values to just a small subset. Okay, so to sum up this part, we saw the idea of clustering, different types of clustering, hierarchical, partitional, different ways of assigning examples to cluster, exclusive, overlapping, and so on, and the different types of clustering. We're going to look at this in more detail in the next weeks, because the different clustering algorithms allow you to choose these different criteria for clustering. So it's important to understand how the different algorithms work and to really think about what you want to do when you are clustering. So which are the best algorithms for your purpose. We saw k-means as a first example. This is a simple clustering algorithm that's easy to understand. We saw also its application to vector quantization and used it to get this intuitive notion of the expectation maximization algorithm. So basically, what we're trying to solve here is to find the parameters that maximize the likelihood of our data belonging to those clusters, but the clusters are not given by the data. So we need this additional estimation expectation step where we estimate based on a previous guess of the parameters where our points should be assigned to. And then based on that expectation, we maximize the likelihood function. So I advise you to read these sections of the Bishop, Alpiden, and Marsland. There are some introduction for expectation maximization, relation between k-means and self-organizing maps, and so on. But this, the important here is thing here is to start thinking about these problems with clustering. What attributes of the algorithm you really need to consider to select the best algorithm for your problem. Okay, so let's take a 10 minutes break. We'll continue at 5 minutes after 5. See you soon.